Handling repeated roots and irrational coefficients. Welcome, everyone. Before we dive into today's new material, let's take a moment to reflect on what we have already covered. In our previous lessons, we focused on solving quadratic equations where the roots were distinct, meaning they were different from one another, and where those roots were simple, easy to work with integers or rational numbers. However, as we move into more advanced mathematics, we often encounter more complex scenarios. We frequently run into special cases where the roots are not distinct, meaning they are actually the same value, or where the coefficients in our equations are not simple integers, but involve more complicated numbers like square roots. In today's tutorial, we are going to master how to handle these two specific situations. We will specifically focus on two scenarios. First, how to deal with repeated roots, and second, how to solve equations involving irrational coefficients. Let's get started. 1. Repeated roots, perfect square trinomials. Usually, when you solve a quadratic equation, you expect to find two different answers or two distinct roots. However, there are specific instances where both of those roots turn out to be exactly the same. This happens whenever the quadratic polynomial we are working with is a perfect square. To understand the concept behind this, let's look at the structure. If we have a quadratic expression, a x squared plus bx plus c, and that expression can be rewritten in the form px plus q all squared, then setting that equation px plus q squared equals 0 will result in the same value for x twice. Because the two solutions are identical, we use the mathematical terms repeated root or equal roots to describe this situation. We'll see exactly how this looks in practice with a step-by-step calculation in the next slide. Now that we've established that we aren't just looking at simple integers and distinct roots anymore, let's dive into our first special case, repeated roots, which we often see in what are called perfect square trinomials. Step-by-step example, repeated roots. Now that we understand the concept of perfect squares from the previous slide, let's walk through a concrete example to see how this looks in practice. We are going to solve the equation x squared minus 10x plus 25 equals 0. First, let's start with step 1, where we identify our coefficients. Looking at our equation, we can see that a equals 1, b equals negative 10, and c equals 25. Next, in step 2, we need to find two specific numbers. These numbers must multiply to give us the product of a and c, and add up to our middle coefficient, b. So, our product is 1 times 25, which is 25, and our sum must be negative 10. If we look closely, the two numbers we are looking for are negative 5 and negative 5, because negative 5 times negative 5 gives us 25, and negative 5 plus negative 5 equals negative 10. Moving on to step 3, we use those two numbers to split the middle term. Instead of writing negative 10x, we will write it as negative 5x minus 5x, so our equation becomes x squared minus 5x minus 5x plus 25 equals 0. In step 4, we use the method of factoring by grouping. We'll group the first two terms together and the last two terms together. From the first group, we can factor out an x, leaving us with x times the quantity x minus 5. From the second group, we can factor out a negative 5, which also leaves us with the quantity x minus 5. This gives us x times the quantity x minus 5 times the quantity x minus 5, all equals 0. Since both terms share the same binomial, we can simplify this to the quantity x minus 5 times the quantity x minus 5 equals 0. Now in step 5, we apply the zero product property. This tells us that for the product to be 0, at least one of the factors must be 0. So, we set the first factor, x minus 5, to 0, which gives us x equals 5. We do the exact same thing for the second factor, x minus 5, which again gives us x equals 5. To conclude this calculation, we see that our roots are x equals 5 and x equals 5. Because both values are identical, we officially say that the root, x equals 5, is a repeated root. To give this some real-world context, imagine you are designing a square garden plot. If you simply knew the area was 25 square meters, you would solve x squared equals 25, which leads to x equals 5. However, in more complex design problems, where area and perimeter constraints are linked, you might end up with a perfect square equation like the quantity x minus 5 squared equals 0. In such a case, it implies there is only one unique physical dimension for the side of your garden that satisfies all your specific constraints. In the next slide, we will see how this same logic applies when the numbers aren't so simple and actually involve square roots. 2. Solving equations with irrational coefficients. As you can see on the slide, sometimes the coefficients, our A, B, or C, involve square roots, also known as radicals. I know that seeing square roots inside a quadratic equation can look quite intimidating at first, but don't let that discourage you. The beauty of algebra is that the splitting the middle term method we used in the previous examples still applies perfectly here. The real secret is simply being very careful with how you multiply and factor these radicals. Let's walk through a concrete example together to see this in action. We want to solve the equation square root of 2 x squared plus 7x plus 5 times the square root of 2 equals 0. First, let's identify our coefficients. Here, a equals the square root of 2, b equals 7, and c equals 5 times the square root of 2. Next, we need to find the product of a and c. When we multiply the square root of 2 by 5 times the square root of 2, we get 5 times the square root of 2 times the square root of 2. Since the square root of 2 times the square root of 2 is simply 2, our product simplifies beautifully to 5 times 2, which is 10. Now we follow the same logic as before. We need two numbers that multiply to 10 and add up to our middle coefficient, which is 7. Looking at the factors of 10, it's clear that the two numbers we need are 5 and 2, because 5 times 2 is 10, and 5 plus 2 is 7. With those two numbers, we can now split the middle term. We rewrite our equation as square root of 2 x squared plus 5x plus 2x plus 5 times the square root of 2 equals 0. Now let's use the grouping method. We'll group the first two terms together and the last two terms together. This gives us the quantity square root of 2 x squared plus 5x followed by the quantity 2x plus 5 times the square root of 2. From the first group, we can factor out an x from the second group. Here is the tricky part. We want to find a common binomial. Notice that the number 2 can be written as the square root of 2 times the square root of 2. This allows us to factor out a square root of 2 from the second group. When we do this, we are left with the expression x multiplied by the quantity square root of 2 x plus 5 plus the square root of a 2 multiplied by the quantity square root of 2 x plus 5. See how both parts now contain the same binomial? We can factor out that common term, which gives us our final factored form. The quantity square root of 2 x plus 5 multiplied by the quantity x plus the square root of 2 equals 0. Finally, we apply the zero product property to solve for x. We set each factor to 0. For the first part, square root of 2 x plus 5 equals 0, which leads to x equals negative 5 divided by the square root of 2. For the second part, x plus the square root of 2 equals 0, which gives us x equals negative square root of 2. So, to conclude this example, our two roots are x equals negative 5 over the square root of 2, and x equals negative square root of 2. It looks complex, but if you follow the steps, the radicals resolve themselves quite naturally. Now that we've mastered how to handle repeated roots, let's move on to a slightly more challenging scenario: solving equations with irrational coefficients. Common mistakes to avoid. First, let's talk about incorrect radical multiplication. When we were working with those irrational coefficients in the previous slide, a very common mistake is calculating the square root of 2 times the square root of 2 as 2 root 2. Please be careful here. The square root of 2 times the square root of 2 is simply 2. A good rule to keep in your head is that the square root of n multiplied by the square root of n always equals n. Second, regarding the repeated roots we discussed earlier, many students tend to ignore the second root. When you solve an equation and find that the answer is 5 and 5, it is tempting to just write down x equals 5 and move on. However, from a mathematical standpoint, a quadratic equation always possesses two roots, even if those two roots happen to be identical. So, always acknowledge both. Finally, there is often difficulty in grouping when radicals are involved. As we saw in our step-by-step example, when you are looking at an expression like 2x plus 5 root 2, it might not be immediately obvious that root 2 is a common factor. If you're stuck, try rewriting the integer part. Remember that 2 can be expressed as the square root of 2 multiplied by the square root of 2. This little trick can help you reveal the common binomial factor. Now that we have worked through those two different types of equations, I want to pause and highlight some common pitfalls. Even if you understand the logic, these small errors can easily lead to the wrong answer. In our next and final slide, we will summarize everything we have learned today to ensure you have a solid grasp of these concepts. Key takeaways. All right, we have reached the end of our tutorial. Let's take a moment to recap the key takeaways from today's lesson so you can consolidate everything we've learned about handling these more complex quadratic equations. First, let's revisit repeated roots. As we saw in our first example with the perfect and square trinomial, repeated roots occur specifically when the quadratic expression is a perfect square. This means that when you factor the equation, you'll find that the two linear factors are exactly identical, which results in two roots that have the same numerical value. Next, regarding irrational coefficients, don't let those square roots intimidate you. The fundamental method of splitting the middle term remains exactly the same as the simpler equations we studied previously. A helpful tip to remember is that when you calculate the product of A and C, the radicals often multiply together to simplify into a rational number, which actually makes finding the split much more manageable. Third, I want to emphasize the importance of radical manipulation. When you are working through the grouping stage, especially when coefficients involve radicals, remember the trick we used in our second example. Any integer n can be expressed as the square root of n multiplied by the square root of n. Keeping this identity in mind is crucial for identifying common binomial factors during factorization. Finally, no matter how complex the coefficients appear or whether the roots are identical or distinct, the ultimate goal remains the same. You must always apply the zero product property. This means your final, essential step is to set each of your linear factors equal to 0 to solve for your variables. I hope this summary helps clarify these special cases. Keep practicing these techniques, and you'll find that even the most intimidating quadratic equations become much more approachable.